плохо пока. Так. А если так? Или хорошо? Раз. Так. А если так? Окей, вот у нас не работает. Раз. Я, кажется, смог сделать видео и запустить трансляцию. Звук пока идет неправильно. Но...
Если будет видео без звука, то точно не стоит.
Нет, там...
Это несерьезно.
Там звук есть, но он просто идет с компа.
Я не знаю, есть смысл это делать синхронно.
Ну,
Нет, все равно.
если хотя бы семинар запишется, то будет лучше, чем ничего.
How can we prove that a space doesn't have torsion in Gayfullin? Is there in general?
Generally, this is. Ardor proved this from spectral sequence.
Раз,
He proved that spectral sequence.
раз.
Non-trivial differentials. And once he proved this, this is immediate. The matter is that we have no torsion in the base by the induction, or we have no torsion in the fiber. And
Раз.
if there are no non-trivial differentials, then
Раз.
immediate. I tried to prove this without spectral sequence, so I tried to avoid this argument. But if we don't know that there are no non-trivial differentials, then it doesn't follow that when you have non-trivial differentials, torsion may appear, even if there was no torsion in the base of the fiber.
Все, со звуком тоже разобрался, он теперь работает. Вот, так что если вы не против.
Я не против. Повторять, конечно, не буду. Все, нет, это так надо. Okay. Well, let's proceed.
Unfortunately, because of some technical reasons, there were no translation for the first type and no recording for the first part of the lecture. So I just want to say that we are proving this theorem due to Vladimir Igorevich Arnold, 1969, on the cohomology of pure braid groups. And at the moment, we are proving that the cohomology classes corresponding to forgetting all strands but the two satisfy these relations, and we need only to work with pure braid group on 3 strands. And one more improvement which I would like to have here, that actually I have already said this, just I want to make my notation more clear. Look, omega ij is just, it acts on, its value on generators is as follows. So we just compute, this is so-called counting homomorphism. We just compute the number of letters tau ij, but the algebraic number in a word. Any element of a group can be written as a word in these 3 letters, and we compute algebraic number of A, of B, and of C. So I would like to denote it like that, that omega 1, 2, well, we compute the number of letters C. I denote it by n with index C. Omega 1, 3, it's for letter B, and omega 2, 3, it's for letter C. So A. N just means that I compute the number of such letters, algebraic number of such letters in a word, and since it is easy to see from all these relations that these homomorphisms are well defined. They are independent on the choice of a word which represents an element. And our relation writes as okay, what is this? NA and B plus NB and C plus NC and A equals 0, but it is important that it is not a relation among functions on, here we have cohomological multiplication. I prefer to be precise here. Well, it is not the same as we just consider this as a function on a group and multiply one function by another in standard way. Of course, this is different way thing. We mean cohomological multiplication here. Okay, this is what we want to prove. Okay, let us start with a general observation. Suppose we have 2 homomorphisms which I would like to write down this relation in bar resolution. Suppose that we have 2 homomorphisms, well, rho and sigma, from some group to Z or to any other commutative ring, it doesn't matter, to coefficients ring, but let it be Z. And I'm interested in rho multiplied by sigma in cohomology. And I would like, we know that cohomology of a group can be computed using these standard K-chains. Well, K-chains of a group with, I recall that K-chains of a group with coefficients in Z is by definition all maps, not homomorphisms, but all maps from of G of n argument in G to Z with a differential which is dual to the bar differential. We have written this several times. In particular, C1 is just maps from G to Z. And of course, it is, I recall that what is differentials from C1 to C2? Differential is delta F, its value on G1, G2, is it is by definition like that, with standard sign minus here. And so it is just f of G1, G2 minus f of G1 minus f of G2. So cocycles are exactly homomorphisms. And this is not surprising. Okay, differential from C0 to here is just trivial in the case of untwisted coefficients. And so it is not surprising that what the result is homomorphisms. It is just like that. So any homomorphism is represented by itself, considered as, regarded as a function. So for these two, we have their description in terms of bar resolution. The question is how to construct the multiplication. But okay, we know general formula for multiplication of cochains and bar resolution. We have deduced it maybe last time, yes. And this is like that. In the case of generally, we need to general formula. We have these G1, Gn arguments, and we just separate them into two parts. In the case of one cochains, it is completely easy. It is again with the same standard minus. It is just rho of G1, sigma of G2. So it is very easy. Okay. This is just standard general formula in our particular situation. But look, this is on the level of cochains. So even if this cochain is non-trivial, it may be trivial in cohomology. And in our situation, if we look on this particular cochain, well, then this particular cochain on the in C2 of Gz, well, this our cochain which we are interested in, its value on, this is 2 cochain, and its value on a pair of elements is just NA of G1. Here, this is multiplication of numbers, not of NB of G2 plus NB of G1 NC of G2 and plus NC of G1 NA of G2. Okay? And of course, as cochain, this is non-trivial. We can easily find 3 elements such that the value, this value is not 0. Well, for instance, if G1 equals A and G2 equals B, then this is 1, this is 0, and this is 0, and the sum is 1. So it happened, it is not, this is not the case, the same case as with the differential forms. On the level of cochains, this is not trivial, non-trivial. But what we are, I claim that this cochain is a coboundary. So we have a 1 cochain such that this is delta of this 1 cochain. How to invent this 1 cochain? First of all, delta is written by such formula. So if we invent some 1 cochain, then we need to compute its delta like that. And our goal is to find such f. F now is not a homomorphism, some function on a group, which behaves like that, that if we take delta of this f, then we get this right-hand side. Well, here is a very useful trick which works in different situations. Now maybe this one is the simplest when it occurs, but generally it also works sometimes. We can consider more complicated next level counting functions. Look, here we have counting functions of just of letters A in a word, or of letters B, or of letters C. We can consider more complicated counting functions. Namely, suppose that you have a word W is a word in A, B, and C with inverses. Then I would like to introduce such counting function. I denote it by NAB of W. What does it mean? I consider all this word, well, A cubed, B, C squared, A minus 5, C, and something like that. And I count all pairs A and B in this word, such that A is before B. But again, algebraically. So if I see a pair not AB but A inverse B, then I count it with -1. If I see A inverse B inverse, then it's again 1. So A B plus 1, A inverse B -1, A B inverse -1, and A inverse B inverse 1. With any other letters in between. This is just any such pair gives impact 1 to this counting function. But look, if B is before A, then it doesn't give us 1. Well, so I define this function. Look, this function is well defined on words in free group. An element of a free group is also not just a word, but a word in which we are allowed to add or to delete A inverse, and so on. But inserting A inverse in any point, we do not change our function. Well, the matter that with each B, this A and A inverse give opposite. So this one is well defined as a function on free group with 3 generators. But look, our group is not free. We have these relations, well, and so these functions are not well defined. Look, for instance, NAB, here it is -1 on the right hand side, and on the left hand side it is 0. So this function is not well defined on our group. But it is a standard situation that functions like that are usually not well defined on interesting groups. But they can be used as building blocks to build well-defined functions. And in this particular situation, it is very easy to see a function which is well-defined. I claim that this function is well-defined. Again, on free group, each of the summands is well-defined. And we need only to check that replacing any subword like that by a subword like that doesn't change the total value. And similarly for, okay, the second two are just by symmetry. We need to check only for this one. since we have this cyclic symmetry. Look, first of all, well, suppose we have a lone word. I write it here. Suppose you have a lone word in which you have such fragment C, B, C inverse. And I would like to replace it by the same word with fragment A inverse B A. When I compute the value NAB, I need to compute not only this AB, I need to compute all A and this B. Well, but such in exterior A and B, where, or maybe A here and B here, they are just the same here and here. So I only need to check impact of this particular just in such interior where at least one of the letters is far away. Then look, if you compute, for instance, BC, well, then here we have C, which can appear with different B's. But BC and BC inverse, they cancel. So it is okay that here we have no C. So all such pairs which with at least one letter outside this region, they easily cancel. But in this situation, we see that for this small fragment, we see that NAB equals -1, okay? NBC equals 0, and NCA equals 0, okay? And here we see that NAB equals 1, NBC equals -1, NCA equals 0. So it's well defined. The sum is well defined. And similarly for the two others, this is just using cyclic symmetry. So this function is well defined on P3. But this is only function. This is only a function. This is not a homomorphism, of course. There is no reason for it to be a homomorphism. And moreover, it is natural to compute the differential of this function. This is a well-defined function. This is a one-K chain on this group. So it is natural to compute the differential of it. I think I clear the claim of the theorem. Look, if you compute the differential of this function, okay, if I would like to compute it on two elements, well, for a moment, now I want to write down the thing which is not well defined on P3. But for a moment, let us represent these elements by particular words. I would like to write something which is defined on words. Well, but generally, what I need to write? I need to write this function on the product minus this function on G1 minus this function on G2. But once I choose these words, I can write it separately for each summand. So I want to write this for NAB of multiplication of these two words minus NAB on W1 minus NAB on W2 and plus the same, well, I would like to write plus cyclic permutations of A, B, C. So the same for BC and the same for CA. When I write particular words, then it is well defined. But now let us look on this. I have two words, W1, and I want to make a drawing not here. The matter I would like to continue with this formula. I would like to draw it here. I have W1 and I have W2. Look. And I would like to count all pairs AB in the total words, such as A is before B. But then I would like to count all such pairs in W1 and to subtract it. And then similar pairs in W2 and also subtract it. This means that all pairs like that will cancel. And all pairs like that will cancel. And the only type of pairs which still here is when A is here and B is here. But then it's the algebraic number of A is here times the algebraic number of B is here. So I say that this is an A of W1, but here I can return to our group elements. The matter is NA is well defined on the level of group times NB of G2 plus NB of G1 NC of G2 plus NC of G1 times NA of G2. Well, we see that this is exactly what we need. So this cochain is a coboundary, and it is the coboundary of such nice function, which is, well, so such tricks of such type are sometimes useful, and so this is why I hope that, of course, Arnold's argument is more natural. So it is more clever and more natural. Instead of such trick, just use differential forms. But this sometimes also can be useful. So I think that this is. And this argument works without any assumption on torsion. So we definitely know, even we still do not know that there is no torsion in this ring, but we already know that, so we have proved this, that our classes omega ij do satisfy these relations. Well, now I'm going to prove we are going to prove this second and third assertions, but before proving them, let us look on some consequences of them. The matter is that I would like to prove these two by induction, and it is convenient to use some consequences when proven by induction. So assume for a moment that we do know this theorem. What then we see? What, in fact, we see? First of all, we can describe an additive basis of this cohomology ring. So if we know this answer, that the cohomology ring is the quotient of such exterior algebra by all relations of the form that I have written. It is natural to ask, well, let us study this right-hand side. So what is this if we take the exterior algebra generated by all these elements, modulo all these relations star? Of course, this is a finite dimensional, just finitely generated abelian group, if we forget about multiplication. I claim that it is not so hard to describe the basis, a basis of it. And a basis is so proposition. This is just purely algebraically a proposition about this ring. Proposition is that the following elements constitute a basis. We need to take all such monomials with the following restrictions. That first of all, ki is less than li for all I. And second, these maximal indices are ordered. So claim is that such monomials constitute the additive basis and an additive basis of our ring. Let us denote it, say, R. Okay, in fact, to be honest, I need only one part of this. I need only that these elements generate additively the ring. Well, what should I prove? I should prove that if I have any monomials in omega ij's, then I can, using these relations, I can transform these monomials to the sum of monomials of such kind. Well, this is very easy. First of all, if I am interested only in exterior monomials, so that if some omega ij enters at least twice, then it is just 0. We have this anti-commutation. Oh, sorry. This is actually another good point. The matter is that we may ask, are we sure that omega, I forget about this. We also are interested in this situation, whether it is true that it is 0. Let us stop for a moment and discuss this. The matter is that when we or generally, if we speak about one-dimensional cohomology classes, then, okay, they anti-commute. So omega ij, what we see that omega ij equals minus omega ij. So we only know that this element has order 2. And this is a good question. Why this is actually 0? This is a rather easy question. I hope that you can tell me. Well? No, Tij square is not 1. It's just twice twist. y. Yes. Whoa. What's the cohomology of Z? It's the same as cohomology of the circle. So it's definitely true in P2. And it is enough to check it in P2. So it is true in this group, since there are no second cohomology, and hence it is true in any group. And actually, it is true always. If you have a one-dimensional integral cohomology class, then the square is always 0. And this is again, since it is true in Z. So there is no problem with this, and we may forget about all these elements of order 2. And so, okay, monomials with at least one omega KL entering twice cancel. They are 0. Moreover, we can always arrange our, we can always permute this up to sign. And so we can always achieve that any monomial can be taken to this form with L's, with K's less than L's, and L's non-strictly. We can always arrange that they increase, but non-strictly. The only thing is that we would like these to be strictly increasing. How can we achieve this? So we just can look on, suppose that at some point we have a non-strictly increasing situation. So we have, let it be some PQ, and then P with some L, okay. And the next one is again, P and Q are just some K's, and L is the same. We have this. But we know that using our relation, we can rewrite this as, okay, we can permute this L and Q, this doesn't matter. And so we can rewrite this as omega L, okay, let us be precise, omega PL, omega LQ, and now I would like to make two cyclic permutations of PLQ, so minus omega LQ, omega QP, minus omega QP, omega PL. Yes, and from the very beginning, P less than L and Q less than L. Yes? What we see here? We see here that, okay, we can swap these two, and we get omega QP, omega QL, minus omega QP, omega PL. Okay? And we see that here maximal, only one L, only one maximal index L, and the second maximal index in each of the of our monomials becomes less than L. Okay, it may happen that we still have several with the same index, but the problem is moved closer to 0. So applying this procedure several times, we arrive to a monomial with strictly ordered LIs. Good combinatorial exercise to prove this proposition completely. So to prove that there are no, we have no more relations. I don't want to do this now, but it is not so hard. Actually, we will prove that. We will prove this too, and it is more than this. We know that. Well, not completely, but actually, I prefer to do as follows. Well, okay, it's a good exercise to show that these are linearly independent in this ring, and another good exercise is that we actually do not need this in our further proof. Okay, and another next next thing which I would like to check is that, okay, once we know this additive basis, we can compute the rank of each homology group, cohomology group. We see that, okay, once since we know the basis, we at least know that this group is free abelian, and we may ask about its rank. And it is the result can be easily formulated in terms of Poincare series. We can always, it is often useful to consider the following for any space with finite rank cohomology group or homology group. We can consider such series of formal variable t, which is just sum over n rank of hn. I prefer another letter, hk, of some space or group, say with z coefficient, times t to the power k. We can use this for homology, for cohomology with different coefficients. Instead of this rank, it's often with for a field, then we just write dimension. But in our situation, we have finite groups, finite generated abelian groups and free abelian groups. So it's natural to write like that. And it is often easier to write down such Poincare series than to write down particular formulae for ranks. In our case, I claim that the rank is for this ring. So for Pn, if we have already proved the Arnold's theorem, the result is as follows. It's 1 plus t times 1 plus 2t plus, and so on, 1 plus n minus 1t. So rank hk of x, z is equal to coefficient of t to the power a, k in this series. There is no good formula for this. But, okay, we can compute any. Why the result is as follows? Well, look, any such, how many such monomials with given L1, L2, Ls? We have sorry. No. This is not a good question. Just it is better to see this inductively. Look, First of all, this is true when n equal 2. Yes, when n equal 2, we have only one summand, 1 plus t, and we already see that, for the group pp2 equals z, and we have one-dimensional cohomology in dimensions 0 and 1, and this is exactly like that. When we come from Pn minus 1 to Pn, then we need to add all such monomials with Ls equals n. All others are already there, but we need to add those for which Ls equal n. And how many of them are there? We have the same number of monomials with indices less than n, and we have n minus 1 possibilities for Ks. So this is exactly all old monomials, and these are new monomials. Their degree is 1 greater than the degree of which is such monomial, and n minus 1 corresponding to n minus 1 possibilities for Ks. So once we know the additive basis, we immediately see that the Poincare series is like that. And what I would like to add here, and this last assertion will also be used in our induction. So I would like to prove all this by common induction. And the fourth is about homology of pure braid group, Pn. What I know the universal coefficient theorem, that cohomology is obtained from homology by Homs and Exts. Exts move once. If we knew that homology is finitely generated, then the only possibility to get free abelian groups in cohomology is to have the same free abelian groups in homology. But if we do not know about finite generation, then it is not so obvious. What I would like to say here, I claim that homology groups of Pn Z are free abelian. Actually, are finitely generated, and hence they are free abelian of the same ranks. And hence free abelian with the same Poincare series, with the same ranks. As for cohomology, with the same Poincare series or with the same ranks, so with this particular Poincare series. So I'm going to prove all these three, and this immediately implies, once we know that homology groups are free abelian, then we have immediately from universal coefficients theorem that pairing between homology and cohomology is non-degenerate in each dimension. So cohomology is just Hom from homology to Z. This is direct consequence of that. And my goal is to prove these three assertions by induction on n. Of course, all of them are true for n equals 2. It is easy. And so we may start with the induction. And here is another useful trick. So one moment, I want to look on my, there are some signs and formulas which I don't remember. Okay. Now again, I would like to work in bar resolution. And let us change notation for bar resolution. The matter previously I denote bar resolution either by Pn or by Fn. And now both symbols are busy, are already occupied. So I prefer to denote the bar resolution by Bn since it's bar. But also I would like to consider bar resolutions for different groups. So I will use this notation for bar resolution for group, not for, actually even not for, this is bar resolution, but what I'm interested in, first of all, I take normalized. This will be normalized. However, actually, it doesn't matter whether it is normalized or not, but let it be normalized, it doesn't matter. But I'm mostly also, let it be C star of G. It's the chain group of BG. So it's just bar resolution tensored over G by Z, as we always discussed. So this is just the complex using which we compute their the homology of our group. And what I want to check, actually, I would like, well, now I will prove several claims. In all these claims, I always assume the theorem for smaller n's. So I work with some particular n, but I assume, let us fix it here, assume the theorem for Pn minus 1. So I would like to prove that these monomials are linearly independent in cohomology. So claim which I would like to prove is that such monomials as written with ki less than li and L1 less than L2 less than Ls. All such monomials are linearly independent in cohomology of linearly independent in cohomology of Pn. And I know that these monomials, such monomials with Ls smaller than n, are linearly independent in cohomology of Pn minus 1. Okay? And look, what I recall that I've got such an exact sequence. We have already discussed it. But also, this sequence splits. And what does it mean? This means that map in cohomology, this projection is pi, the pullback in cohomology must be injective. Since it splits, we immediately see that it's injective. And hence, we already know that if we consider such elements with Ls strictly less than n, then they are linearly independent. So let us fix this. Those monomials with LS strictly less than n are linearly independent. We would like to prove linear independence of all of them. And here is another nice trick. Another nice trick is the existence of the following I would like to take an element in Pn, and to an element in Pn, I would like to associate some special mapping from chains of Pn minus 1 to chains of Pn, but from chains, order of chains increased by 1. I put P here and P plus 1 here. I would like to invent one particular mapping for which I hope that some good properties exist. But I would like not to start not with properties, but with particular formula. To write down this formula, it is convenient to introduce the following notation. It's standard group notation for conjugation. It is often useful to write like that. X to power y is y inverse xy. Well, first of all, this is an automorphism, so x1 to the power y, x2 to the power I, y is like that. And of course, x to the power y to the power z is equals to x to the power yz, and hence these natural properties make this convenient notation. Now, I would like, my main idea is as follows. I would like, well, if I have any element in bar resolution, okay, I always mean by resolution tensored by z. So it is free. It is basis of bar of this group as of abelian group, not as of module. Okay, the idea is to add here h. Signs are better if I add h from the left, but for me it is convenient to add from the right for further considerations. Well, since here we have this from the right, just to be okay. The first idea is just to add here this h, but this is mapping with a rather bad. I would like to have such mapping that it will rather good. It is rather its relationship with differential is rather good, and the idea is the following: that now I would like to proceed, and I would like to insert h in different places, but so I can write g1, g p minus 1, then I insert h, but now look, when I take the differential, here gph appeared. If I put gp here, then hgp appeared. This is not the same. But I prefer to put here gp to the power h. Then, multiplying these two, we get gph. No, but not hgp. And so on. Next, signs alternate. Next one is g1, gp minus 2, h, g1, gp minus 1, to the power h, gp to the power h. Minus and so on. And the last summand will be h on the first place, g1 to the power h, gp to the power h, and it is easy to see that this sign is minus 1 to the power p. Okay? Well, this is formula. I claim that such map is rather useful, and it satisfies good properties. What are good properties? To understand these good properties, I suggest that we compute the following. I suggest that we make such calculation, and I suggest we calculate the commutator of this with the differential. Well, I understand that it is not so nice to make such computation late in the evening, but let us try. Well, to avoid actually cumbersome situation, let us do it for p equals 2. We do it for p equals 2, we see the answer, and then it is more or less immediate to check that the same is true for arbitrary p. Okay, I can do it myself. If there is a volunteer who can help me, it would be nice. If not, I try to do it myself. Okay. No, I suggest we first consider. Yes, the first one. No, I suggest not to do this. It's yes. No. We are already here. No G1 in front. This is, yes, this is just. Yes. Yes, G1 and. Yes. So, yes, similar for terms for each of these. Plus. Yeah, we have general minus. Yes. Yes. Oh, no. They are separated by bar. G1H, bar G2H.
This will be
here we have this, yeah.
Yeah, here we have this, yes.
And minus h given.
Okay.
Yeah, and nothing below.
Let us cancel what is possible. Oh. This agreement was to just, okay, GPH cancels with HGPH. This is exactly why something must cancel. But this conjugation is exactly to provide that something cancels. Look, this one and this one.
Oh. Yeah,
And also,
maybe.
yes, it's better to cancel them at all. And one more situation. Yes, that's all. You can erase everything. Yeah. Let's just erase this. Yes, yes. No. No. In opposite, H before this. And now we need to subtract from the left blackboard to those which is written on the right.
Okay, let me write.
Yes.
And yes, this is 3. And this is 4.
Yes.
So
And so you may answer. It's better to write it here.
so here reconstruct everything. So G2.
No.
Oh.
This,
Here. So it's minus G1. Just plus 4.
well, yeah. Thank you very much. This is a very nice answer. Look. Of course, once you have well, once once you have this once you have such a chain, you can always use conjugation by H to produce another cochain. And these two cochains are homotopy equivalent. This HAH is homotopy equivalence between trivial map and this conjugation map. The answer is similar for any other for any other P. I just would like to write down the result. Only signs differ, the same. Well, I think I erased this computation. It's very useful, but well, we see the answer. Now I erase it. And what we get generally is, now I would like to write a correct sign. Well, minus AH D applied to G1 GP is just minus 1 to the power P Actually, we could choose the sign of AH just to obtain 1 here, but it doesn't matter. Well, what is it about? Well, first of all, this is such chain homotopy, and it can be such chain homotopy can be used not only in this situation. It is well, this formula is generally useful. It is useful whenever we need an explicit chain homotopy between these two guys. Now, why this is interesting for us? Assume that we have got a chain in the group Pn minus 1. So, look, since we know by induction we know the cohomology and homology of Pn minus 1, we may take this Xi. First of all, I would like that this Xi is closed. And second, I would like that it represents some particular homology class. I know homology, so I can take, for instance, that Xi is dual to some particular basis element. Dual, okay, once I have this basis in cohomology, I have dual basis in homology. So I can take dual element in homology but now these LI's are less than n, strictly less. So R is, yes, sorry, why I need two different letters, I would like to have the same letter. But this LR is strictly less than n, since it's, but now the idea is to try to construct the time is rather over. Well, so I say some idea and we finish for today. The idea is to take some, for instance, I'm interested in monomial, which is like that, and also I'm interested in such monomial Kp Lp, and here some Kp plus 1 n. I know what happens with monomials up to n minus 1, but I'm interested in monomial where we have n here. Then I would like, starting from this chain, I would like to write down a chain here, which is closed, and which will have such that this monomial will have non-trivial value on that chain. And the idea is to add, well, okay, we can choose some element h such that the value, for instance, we take for h just t k plus p plus 1 n. So we take such element that this value is non-zero, for instance 1, and we try to write a h of xi. What do we see? We see that this is not completely a cycle. What can we see about it belongs to this group Cp plus 1 of n of Pn, but it is not a cycle. But what is its boundary? This one is 0, since dxc is 0, and so we only have this xi, and we have well, up to sign which I don't want to worry about. This is xi conjugate by h. Each element in bar resolution is conjugate by h minus xi. Well, and next we need to apply some more efforts to add something to provide that the boundary is 0, and then if we do this, look, this first summand makes non-zero income to here. The matter is that here the value of the last homomorphism is non-zero, and here the values of previous are previous homomorphisms have non-zero value on xi. Here all other summands give 0 value. The matter is that on all these elements the value of the last homomorphism is trivial. So we expect to have non-zero value, but let us postpone it now. So we may use such chain homotopies to construct new homology classes explicitly. But okay, at the moment let us stop now, since we have very few times.
So using this, we will prove 2 and 3, yeah? We'll
Yes, if we succeed, we will prove, no, we will prove 2 using this, not about 3. And actually, as for 3 and for 4, it is not so easy. Here, the argument is more or less topological. The matter is that if the argument is topological, the matter is that if we look again on that homotopy fibration, here the fiber is R2 without n-1 points, but up to homotopy, the fiber is wedge of spheres. And actually, this fibration can be up to homotopy. It can be made that just its true fiber is one wedge of spheres. And then it is not so hard to prove that this configuration space has cell decomposition with how many cells? You have as many cells as here, plus each of these cells is added to dimension and 1 dimension higher in n-1 examples. And this means that if you just look on cells, then the Poincare series for cells is like that. So homology cannot be larger than cell groups. So if we already know that, if we know 2, then 3 and 4 are more or less explicit from such topological observation. That actually we have the same situation as, say, for RP infinity with integral coefficient, with the 2 coefficients. Any cell gives a homology class. And there cannot be more homology classes than cells. So if we have as many basis elements as the number of cells, then of course they generate everything. So here the idea is more or less like that. Okay, but let us postpone it. Unfortunately, I didn't succeed to do it on time. But anyway, I would stress that this homotopy equivalence is actually very useful, even independently of this application. It's very useful in many situations. Okay, that's all for today.